where are we? We're looking at the, we finished the overlap add point of view, and I just reviewed it really. And so now what we're doing is the filter bank summation point of view, where we think of the short-time Fourier transform as a sampled filter bank output. So we'll start with a really simple filter bank built using the DFT, no window, or rectangular window you could say. And then we'll go introducing the more general features such as an arbitrary window and an arbitrary hop size. And that'll give us a filter bank with different filters, different channel filters, and also different sampling rates coming out of the filters. So then we'll finally look at the modifications, the time-varying modifications, and as I mentioned previously, it's going to be the dual. They'll behave as a Fourier dual to what we saw for overlap add. So it's interesting that time-varying filtering comes out differently in the filter bank summation point of view, and we'll see exactly how that looks. So here's again the short-time Fourier transform, and this is the brackets are drawn to make it, beg for the overlap add point of view. So you've got a window times your signal, so you take a chunk of signal and you FFT it or DFT it, and you get the nth spectrum. So you get the nth spectral frame, and so we think of it as a sequence of spectra. So there's that picture again. And now what we want to do is reorder the terms in the short-time Fourier transform and multiply the signal by the Fourier transform kernel first, and then apply the window. And so we interpret the Fourier kernel, the e to the j omega t thing, as heterodyning the signal. So it's basically taking the spectrum it centered about omega sub k and translating it down to 0. So this is complex modulation in the time domain. That's a shift in the frequency domain. The frequency domain is circular, so it's a circular shift. The unit circle just rotates. And omega sub k gets rotated to DC. And now we will interpret the DFT sum as implementing convolution of that heterodyne signal with the window. So the window is now behaving as a low-pass filter. And then the hop size, finally, is the downsampling factor. So the time domain output is capital X sub m, so m is the nth sample, and then k is our channel number, so it's a filter bank, and k is the index of the filter in the filter bank. And then we get a time domain signal out, which is capital X sub m, and if we have a hop size r greater than 1, then that's the decimation factor. That's the downsampling factor for that filter bank output. Now, to see this as a convolution, we can write it in terms of these operators, and formally the window is flipped, but our windows are always symmetric, so that's actually not doing anything. But technically, this sum is the convolution of the heterodyne signal, omega sub k shifted to DC. That signal is being convolved with the flip of the window. But the windows are symmetric, so it's just the window. And then finally, we evaluate at the frame number times the hop size. So that's our time of output. Okay, and then if we plot these things, we get filter bank outputs. So here's the 0th channel, this is the DC channel, and each time step is a hop, it's an FFT hop. It's a frame number, so this is the time axis is in frames, or frame numbers, and you can convert it to seconds in the usual way. And then we have, capital N channels of these, so we have capital N complex bandpass filters, and of course we can take the bandpass for omega sub k and the bandpass for omega sub minus k and add those together and get a real bandpass filter synthesized. By just summing those two signals, you're looking at the real bandpass filter output for omega sub k, plus and minus omega sub k. Okay, so let's build this up in a really simple way.